Hello, Lindenwood students. Um, well, things are changing pretty quickly. Um, Hope you're all safe. I've I was working closely with a friend of mine, working on our online classes on Tuesday, and it turns out today he's this is Thursday. I'm doing this. It turns out today he's in quarantine because someone he was working with tested positive. So I hope you're all kind of keeping a social distance, 6 feet. St. Louis has a long history of that. I wish I could get into it, but we really don't have time. Anyway, I know many of you are really struggling with a lot of stuff right now, moving to a new place, trying to find an internet connection, and so on. So I noticed that about half of you are keeping up with these videos, um, and I'm hoping that the rest of you might maybe binge watch. So I'm posting these videos with the idea that even though you may not have time, at least you can get caught up um, if you put in the effort. So anyway, let's keep it kind of mellow today. This is the lecture for Friday. Let me see, Friday, March 20th, I guess, is tomorrow. And so this would be posted Friday, March 20th. So at least let's distract ourselves a little bit with a little bit of stats discussion. Let's review a little bit about what we're doing this chapter. Uh, this chapter is on continuous random variables. And so the probability density function doesn't give the probability for the value of that variable. It's more complicated than that. Oops, I just touched my face. It's more complicated than that. It's the area, the probability that the uh, variable takes on a value around a particular value is the area under the probability distribution function around that value of the variable. So it's more complicated conceptually. Um, the So here's the math speak for that what I just discussed. Let x be a continuous random variable who's got a PDF. Notice that they don't call it P of x anymore because it's not a probability, it's probability density. And the probability that you're in a region between A and B around x is equal to the area under the curve. The area under the curve is a complicated concept. We know formulas for areas of a rectangle, a circle, those kind of things. But these curves have weird shapes, and so the area is a complicated thing. And if you go on and take calculus, you'll see that that's a prime subject matter of calculus. We're not going to do any calculus here. We'll let our machine, our contraption, do all the area finding that we need. Oops. The area under this, well, first of all, that function's got to be greater than or equal to 0 for all possible values of x. Because it's going to give a probability, the area will give a probability. So the area has to be positive. And the total area under that curve has got to equal 1 because the total area represents the probability, all the probabilities added together for all the values of x. And x has to have some value, so that area has to be equal to 1. Okay, so that's the things that we've been talking about in this chapter. So now we get to the most commonly used probability density function that there is. In fact, it's so common that it's called the normal distribution. And it's a bell-shaped curve, and it's sometimes called the bell curve. The bell curve. And I'll probably refer to it as that. It's a kind of a neat name. what the bell curve looks like exactly depends on what the mean is. So here we see mu for the mean. The mean is right in the center. The mean, the median, and the mode are all the same value for this distribution. The mean is the only one we're going to be talking about. And there's also a standard deviation associated with this distribution. So within one standard deviation is all this area here. And we can see that we've been looking at this curve kind of without calling it anything throughout the semester. We called it the imperial curve. But anyway, there's about 68.3% of the probability is in that area there within one standard deviation of the mean. Within two standard deviations of the mean, if I add in this, not this, that's not under the curve, is it? If I add in this and this, I get about 95.5% of all the area. If I add in this piece and this piece, I get about 99.8% of the area. And then there's a very little bit out here underneath the curve out there. And that curve extends all the way to infinity. In this direction, that little sideways 8 is a symbol for infinity. And minus infinity in this direction. It's a mathematical curve, and you can do that in mathematical life. Not so much in real life. It's hard to get to infinity. So here's a little description of this normal distribution. When people talk about being graded on a curve, this is the curve that they're talking about. Okay, the standard it is symmetric. That means it's the same on either side of the mean. And the mean, the median of the variable are always equal. The standard deviation determines how peaked the graph is, how narrow it is. The smaller the standard deviation, the narrower that curve is, right? If I made this graph, this is for any standard deviation. If I cut the standard deviation in half, the peak would narrow down like this. And it would get taller too, because the area still has to be 1. I'm just kind of sketching it in here. So there's a more narrow normal distribution that's got a smaller standard deviation. Looks like it's drawn by someone who's in that vulnerable old age group, which I am. Anyway, when sigma is small, most of the area lies near the mean. These notes are missing some words, so I'll add them in. This results in a high peak and small tails. All right, what else? When sigma is large, when the standard deviation is large, the area is more spread out. This results in a shorter peak and longer tails. Okay, the total area of under the curve is equal to 1. Right? That's something that we all ought to know. That has to be true no matter what the mean or standard deviation is. 50% of the area, I think we can guess some of these things, is to the left of the mean. I'll put it in here. To the left of the mean. I'm just using mu here to symbolize the mean. Oh, I'm supposed to put it in this little blank here. And 50% is to the right of the mean. About 68.3% is between the mean minus 1 standard deviation and the mean plus 1 standard deviation. That's what I described in the picture. In which within IE, that means that is within 1 standard deviation of the mean, in words. See, what we've been working towards in this class is just the language to use to describe these things. I mean, this is all new language to you. About 95.44% of the total area is between the mean minus 2 standard deviations and the mean plus 2 standard deviations. i.e. within 2 standard deviations of the mean. And then about 99.8% of the probability is within 3 standard deviations. Within 3 standard deviations of the mean. Okay, so that kind of lays out the basics. All right. Using a TI 83 or 84 to calculate the normal CDF. So we're never going to use the PDF version of the normal. We're only going to use the command, it's on the calculator, normal PDF, but you're just never going to be pressing it. We're only going to use the CDF version of that because it's going to calculate the area between 2 values. So here are the directions, and that's fine. We'll leave them there. I'm not going to read the directions to you because they don't mean much unless you've got a calculator and you're seeing them. So, and here are the directions to find the inverse normal function. And once again, these directions are going to mean a little bit more to you later, perhaps, when we get to examples. I'm just have them in here as reference for you. I don't need the directions. I probably remember how to use these commands. It's been a while, about a year. Okay. If an adult U.S. male is selected at random, find the probability. Oh, first of all, the height of an adult male in the United States is approximately normally distributed. Okay, that means we're going to use the normal distribution here. And it's got a mean of 69.3 and a standard deviation of 2.8. Find the probability that if you pick a male at random, find the probability that his height will be more than 69.3 inches. Okay, so we want the probability that x will be greater than or equal to, the probability that he has exactly a 69.3 inch height is 0. So we're always going to use greater than or equal to here. Whether it says more than or more than or equal to. It's not going to matter in this chapter. More than 69.3 inches. Okay, I can guess the answer to this because 69.3 happens to be the value of the mean. So the probability that you have a value greater than the mean, let me draw my little bell curve here. Here's the mean. Here's x. Here's the mean, 69.3. What is the probability that you're over here in a height that is bigger than 69.3? Right? See, all these values of x are bigger than 69.3. All these values are less. Well, now you might be able to guess the answer to this. The probability that you're going to be over here is equal to 50%, or 0.5. All right, let's see how we would do this on the calculator. So I'm going to turn my calculator on, and remember this DISTR, distributions. That's where we found the binomial distribution. Well, that's also going to be where we find the normal distribution. So we're going to press second vars. Oh, there they are right at the top. All right, these are the most common, as I said, the normal distribution shows up in life and in all areas of science, all areas of life. So we're never going to use number 1. So don't ever press it. We're always going to use the CDF. So I'm going to press arrow down to the normal CDF, and I get this. And now some models of the TI-84, more modern ones than this, might prompt you for what you need to put here. But the first thing you put is well, we'll see if I'm doing this right because we know what the answer is supposed to be. It's supposed to be 0.5. So the first thing you put is the lower limit of the area that you want to find. Our lower limit is 69.3. And then you put a comma. Then you put the upper limit. Well, look at my picture here. The upper limit goes all the way to infinity, but you can't plug infinity into this calculator. It doesn't have an infinity button. What you have to do is you press second comma, and that is the double E button. It's for exponential. So I just typed in e to E99. That means that's 10 to the 99th power. And that's pretty close. That's plenty close to infinity. Then I press a comma. So I put the lower value of the area I want to find and the upper value. Then I put the value of the mean, 69.3. And then I put a comma. And then I put the value of the standard deviation. That's 2.8 inches in this problem. 2.8. And then I close the parentheses. And I press enter. Oh, it's 0.49999999995. Well, that's pretty close to 0.5. So there could be a little bit of round off error in the fact that we're not putting in exactly infinity. We're putting in 10 to the 99th power. But that's going to be close enough for us. All right, let's do another example. Probability that it's less than 66 inches. So I want the probability that x is less than or equal to 66 inches. Let me draw my little, I like to draw the curves here when I'm doing these problems. So I'm going to draw my little bell curve. Here is 69.3, and where's 66? That's over here somewhere, 66. So I want the area under the curve all the way from minus infinity up to 66 inches. These pictures are very helpful if you can get used to drawing these pictures. So I want to do the CDF of 10 to the minus 99th. 10 to the minus 99th power is a very, 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 very small number. 10 to the plus 99th power is a very, 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 very large number. So we have to mock up infinity. Oh no, let me see. That's not how you do it. You do minus 10 to the 99th. That's a negative of a very big number. That's minus infinity. So that's the number we're going to use to simulate minus infinity. 10 to the plus 99th is plus 10 to the 99th is the number we're going to use to denote positive infinity. Okay, and then what do I want to stop at? I want to go all the way up to 66. And then I want to put in the mean, which is going to be just like last time, 69.3. And the standard deviation, which is 2.8. Oops. Get that out of the way. Okay, let's see what we get. So I'm going to press second distribution, and we'll press number 2. And the first thing I want to put in is negative e to the 99th. So that's negative infinity. Then I want to put in a comma, and I want to evaluate the area up to 66, the number 66. That's in the problem. And then I want to put in the mean, 69.3. And I want to put a comma and then the standard deviation, 2.8. And then close the parentheses. See if I got everything there? And I get 0.119. 0.119. Okay, greater than 72 inches. Greater than 72 inches. So, let me draw my little curve here. Whoa, my bell curve. And here's the mean, 69.3. Where's 72? That's over here, 72. So I want the greater than 72. So I want all the area underneath here, from 72 out to infinity. You really can't be infinitely tall. This is a mathematical idealization of the real world. So it turns out that mathematically it's convenient to think about people possibly being infinitely tall or infinitely short. So let's see, or even a negative height. Those are all, these negative heights down here are very hypothetical. I'm not quite sure what a negative height person looks like. And that comes from the fact that we're using a mathematical idealization for the real world. And that happens frequently if you think about it. But we're not going to think about it real deeply right now. We're just going to try to function here. So what am I going to do? I'm going to do the binomial CDF from negative infinity. That's negative E99. And then I got to put in my upper limit. I'm going to go all the way up to 72. Oh, no, I'm not. Oh, sorry. I was doing the area over here, right? That's not good. I need to do from 72 up to positive infinity. See, if you have the picture here, it's very helpful to catch yourself in mistakes. So I'm going to go from 72 up to infinity. Where's infinity on my calculator? It's e to the 99th. And then I'm going to put in 69.3, the mean, and 2.8, the standard deviation. All right, so let's see what we get. Second distro, CDF, parentheses, okay. Put the parentheses in by itself. So I'm going to go from 72. This is going to be a small probability because 72 is pretty tall. It's above the mean. 72, then 99. Second comma gives you this e to the 99th power. And then I put in another comma. And then I put in the mean. Whenever you're entering the mean and standard deviation, 69.3, I think it was. You always put the mean in first, then the standard deviation. So 2.8. There we go. And I get 0.167. Okay, between 66.5 and 72.1. So I'm going to do, where's that? Let me draw my bell curve again. Here is 63.9, no, 69.3. 69.3, that's the mean. And where's 66? That's over here somewhere. 66.5. And where is 72.1? That's over here somewhere above the mean. 72.1. So I want this area right here. So I'm going to do the CDF. This is actually easier because I don't need to think about any infinities or minus infinities here. The CDF of 66.5. This is probably a pretty good, this should be a pretty substantial probability. It looks like just from my sketch that I've got pretty much area under the curve there. 66.5 up to 72.1, and then the mean is 69.3, and the standard deviation is 2.8. So I do the normal CDF, second vars. It's very easy to accidentally click enter here and get the wrong one. So always make sure you got a CDF here at the end of your normal command. And then just put in 66.5. And then put in a comma. And then what? Put in a 72.1. And then a comma. And then the mean, 69.3. Comma, and then the standard deviation, 2.8, and then enter. 68%. Oh yeah, that is pretty big. So that's 0.683 if you wanted 3 decimal places. And between 66 and 78, I'm going to leave that for you guys as an example. And then I'm going to shut it down for the day. So hopefully by next week you can maybe binge watch these lectures and get caught up a little bit. We need to stay on track for the course because we've got, you know, a certain amount of material that the school says you cover when you take this class. And it's important to maintain the integrity of the class to cover all that material because the school has to maintain its accreditation or none of these classes you're paying for are worth a nickel. So maintaining the integrity of a class and making sure that you cover all the material that the class has is very important for you. So anyway, stay safe. Wash your hands a lot. Don't touch your face. Don't touch anybody else's face either. And I will see you next week.